Hello, welcome back to physics. I'm going to be going over the three FRQs from this first week one, the practice FRQs that were on Schoology. Expectation, I think, to make this the best video experience, whatever, as we can. Please have your work, so a piece of paper of your work. If you want to take a screenshot of this, here are the answers. They will also be posted on Schoology, but please also have the questions up. They're working on a couple technical things of trying to have the questions on the screen over here, but also do this work here on the whiteboard. So take a couple seconds, pull up the original answers, and then we will get started. Cool. Okay, here we go. This is FRQ week one, number 1. So there are 3 total if you're aiming to get that 5 on the AP test, which you are all capable of if you're doing really good review. Please do all 3. If not, the expectation is that you are doing at least 2 of them. So you can skip forward or backwards in this video to go over each of those. I would also recommend having the AP Physics equation sheet open in another tab. Cool. All right, FRQ number 1. A 5.2 kilogram brass ball is transported to another planet. It is not on Earth. You have the radius and you have the mass. I'm going to write out what I have. I'm going to say mass of the ball, 5.2 kilograms. Mass of the planet, 6.2. The radius of the planet is 3-something, 3.7. 10 to the 6 meters. Cool. Awesome. It says, part A, you need to calculate little g. So what is the gravitational acceleration due to gravity on that planet? We know on Earth it is 9.8. However, based on the mass and radius of other planets, that is different on every planet. The moon is 1.6. We can calculate this based on putting a couple equations together on an equation sheet. We need to find g, like so. So I'm going to find on my handy dandy equation sheet an equation that has g in it. I see g is equal to the force of gravity divided by the mass of the planet. Cool, I have mass of the planet, but do I have force of gravity? No. So I'm going to take another step forward and I find the equation Fg is equal to big G, mass of object 1, mass of object 2 divided by radius squared. This would be your planet. This would be an object on that planet. This radius, in this case, is the radius of the planet. However, it also can represent the distance between 2 objects, which we get to in part F. Cool. I'm going to put these 2 together. I have f of g, and I'm going to put it right here. With a little bit of algebra, I now have acceleration due to gravity is equal to big G, mass 1, mass 2, divided by m, divided by an r squared. Now you're like, what did I mess up there? These need to be switched. Good one, Miss Philbrant. There we go. All right, your mass on of the object on that planet, these cancel. So now we have gravitational field on that planet is equal to big G, mass of the planet, mass of the bigger object, the smaller object canceled out, divided by the radius of that planet squared. Do we have the mass? Do we have the radius? Maybe you're thinking, what the heck is G? Big G is a gravitational constant. If you flip your equation sheet, if you have it in your hand, it's on the back. If you're looking at it on the internet, it's at the very top. That number is given to you. So let's erase this. Feel free to pause this, text me, call me, email me, and you're like, oh, at 2 minutes and 32 seconds, what you said didn't make sense. Please do that. So we have now 6.67 times 10 to the negative 11, that is G, big G. The mass of the planet we have up here, 6.2 times 10 to the 23rd kilograms. We don't need to convert that. Divided by the radius is in meters, no need to convert either. That is squared. This is probably the biggest mistake you're going to make, forgetting to square that. You put that into your calculator and you get 3 meters per second squared is our acceleration due to gravity. On Earth, it is 9.8. On planet, whatever we're on, it is 3. Cool. Part B. Need a bigger eraser. Thank you, Amazon. Okay, B. It says, what is the mass of the ball on Earth? So the mass, remember, is the amount of stuff that something is made of. It's not going to change if you go to space or if you're here on Earth or if you go to the middle of the Earth. It's always going to be the same. So we know the mass is 5.2. On Earth, never going to change. Always going to be 5.2. Even if you go to that other planet, you're still going to have the same mass. Again, 5.2 kilograms. No need to convert. Now you need to determine D. What is the weight? So that, again, is the force of gravity that's pulling you down, is the weight. Force of gravity. We always write that as mg. G, again, is your acceleration due to gravity. Part D, on Earth, we know the mass is 5.2. Acceleration due to gravity on Earth is 9.8 or 10. You can use either. On the AP Physics test on May 14th, they're not going to ask you to test your ability to do math. If you use 9.8 or 10 here, it doesn't matter. I'm going to use 10 for simplicity, so I can do that in my head. That is going to be 52 newtons. Part E, you need to determine the weight. So again, weight is our force of gravity on that planet. So again, we have mg, force of gravity on that planet, but we now know the mass is going to be 5.2. Gravity on that planet is 3. Put that into your calculator, and you get 15.7 newtons. I imagine on the AP test coming up that they're not going to ask you to do a calculation like this. However, they will say something like, compare the weight of the ball on the new planet compared to Earth. And you would say, oh, the gravitational acceleration due to gravity is much smaller, so the weight is going to be much smaller. And you might have to write that out or explain that in some fashion. Cool. Part F. Let's jump to there. Hope you are all doing well. It is freezing cold in my basement, but the racing warms me up. All right, here we go. Part F. What's going to happen to the weight of the brass ball if it were set into orbit around that planet? Justify your answer. So when you're on a planet, you have certain gravitational acceleration due to gravity. The force of gravity is pulling you down to the center of that planet. If you are an astronaut out in space, you will always experience gravity. It's just going to get smaller and smaller as you move further out. So the question says, what's going to happen to the weight? So again, remember, weight is your force of gravity, which is equal to the mass times acceleration due to gravity. In part A, we calculated this based on the radius, how far you are from the center of an object. So as you increase your radius, as you increase this distance, r, and you get further and further away, g is going to decrease. It's never going to get to 0, it's just going to decrease. So to explain this, if g decreases, then your weight is also going to decrease. Further and further away, you feel your weight decreases, your mass never stays the same. It will stay constant. Gravity decreases as well. Cool. That was incorrect. I meant to say radius increases. So if your radius increases, G, gravitational field, decreases, your weight also decreases. Totally sorry about that. Cool. Speaking of G, here's part G. Hopefully this video is recording. Suppose the ball was set into orbit at a radius of 7.4 times 10 to the negative. What is the period of this orbit in hours? Going to now our radius. In this case, it's saying how far the two objects are away from their centers. So we're going to say radius 7.4 times 10 to the 6 meters. No need to convert. Got that right? Cool. And you want to find what the period is. So remember, period is capital T. This is time, and it's measured in seconds. The problem asks you, though, to have this in hours. So we're going to have to convert after we get our answer, because our answer will give it to us in seconds. We need it in hours. Well, that will be our final step. You will likely get points, though, if you set up all of your math correct, and then if you forget to convert, you might lose a couple points, but it's not the end of the world. All right, first, we know velocity is equal to distance over time. I know that equation. It's not on the equation sheet. Definitely memorize that. I know if an object is rotating and orbiting around a planet, it's moving at a constant velocity. The distance it travels is 2 pi r. And the time it takes to make one orbit, we're going to call t, our period. So I can rearrange this already and say distance now is 2 pi r over t, our period. Kind of helps me because we have t, we're looking for t, but what about the radius? Still don't know that yet. So I know when an object is rotating like this, or is orbiting and moving in a circle, we have the centripetal force. We also, and we have centripetal acceleration. The centripetal force is what's making it move around in a circle. It's what causes objects to keep rotating. There is nothing that's attached to this ball that's, for example, tension. In the next problem, when you talk about it rotating, tension is causing it to move in a circle. In this case, we know gravity pulls objects in, and gravity is what makes them rotate, makes them orbit and keep going. Force of gravity on our equation sheet is big G, m1, m2, divided by r squared. Centripetal force for orbiting objects is v squared over r is our acceleration times the mass. Getting a little bit closer. I now have mass. Maybe those would cancel of radius and radius. You could put those together. Velocity. Oh, I already have this equation for velocity up here with the period in it. So perhaps putting these together is going to help me find that period. Yes, these equations work, but my ultimate goal is to find the period here. So here we go with some fancy algebra. V squared, I have this equation for V here already. So 2 pi r, all of those things squared, divided by t squared times the mass divided by radius. That looks kind of ugly. Here, nothing changed. We have g, that is our gravitational constant, m1, mass of the second object. So this is planet and your ball. These can be interchanged, divided by r squared. Doing a little bit of rearranging. Cool. Again, we're trying to solve for period here. We have that squared. Our masses, we have, if we want to get rid of this mass, we can divide it by over here. So we'll have mass over mass. Those cancel. If I have this squared on the outside, I need to square everything inside of those parentheses there. Let me erase this just so we have some extra room. All right, so now we have 2 squared is 4, pi squared is pi squared, r squared, we're going to keep that there. However, I have an r squared divided by an r, so one of these is going to cancel. This then just becomes r, like so, divided by t squared. Got rid of this r, mass is canceled, made this a little bit easier to read. Gm, we still have one mass of our planet, or our object, sorry, over r squared. So again, we're trying to solve for t squared. If you get here, you will get some points for putting those equations together. If you get the final answer, obviously you will get all the points. But just as a reminder, if you're doing some of the work, some of the equations, please still remember that you get some of those points. Now we're going to, let's put these r's together. R squared on the bottom, r on top. To get rid of those, you will multiply. So r times r squared is r cubed. Cool. We want t squared though. So to get that by itself, we will multiply both sides by t squared and then divide both sides by gm. Or just flip them. Like so. We want t, we only have t squared here. To get rid of squared, you're going to take your square root. Our final answer is that. Beautiful. Pi we have in our calculator, the radius, how far away it is from the center of that planet. We know g is our constant, 6.67, and then this is the mass of the ball. So putting those into your calculator, you get, I'm just going to write up answer, you get period is equal to 19983.4 seconds. The answer should be in hours though. To convert our answer to hours, I feel like I maybe made a mistake somewhere. Looks good. All right, so we have, let's say, our 9983.4 seconds. If you have seconds on top, you want seconds to be on the bottom so that they cancel out. I know that there are 3,600 seconds in 1 hour. Seconds cancel, so this number divided by 3,600 will give us 5.5 hours. This was a lot of algebra, a lot of math, and rearranging, so this question obviously will be weighted more than other ones, just to give you that heads up. Cool. All right, FRQ number 2. Very similar, centripetal acceleration, centripetal force, object moving in a circle. So a ball of mass 2 kilograms is attached to a string. Already thinking to myself, tension. The length is 81 centimeters. Always should be in meters, so we're going to say 0.81 meters is our length already. The string is negligible mass. The mass of the ball is 2 kilograms. And it is going around in a vertical circle. Cool. On the diagrams below, draw and label the forces acting on the ball. At point A, and we have point B. Drawing free body diagrams, always start with a dot to represent the object. We only care about the object. We don't care about the hand or whatever that's doing the swinging. So at point A, it is at the top of its trajectory. It is on Earth, so gravity is always going to be acting on the ball. Same with at point B. Always have force of gravity. You can write it as equal to mg if you would like for future calculations. At point A, though, it is at the top. So if it's at the top, gravity is going to be pulling it down. There's also going to be a very slight tension in the rope that's going to be pulling it down to make it continue around in its circle. On the answer key, it shows the arrow like so, labeled as force of tension. AP Physics wants you to start all of your arrows touching the object that you are referencing, all the forces acting on what object. So here we will say this is force of tension. This one, in part B, though, it's at the bottom of its circle. So it's at the bottom and it's coming back up. This time, tension is going to be pulling it up. So these are opposite, these are in the same direction. Cool. Part B. All right, part B. You need to calculate the minimum speed the ball can have at point A without leaving the circular path. So at this point, we're going to say this is point B again. So it's at the top of its circle. We have force of gravity pulling it down, and we have the force of tension. We need to find the velocity, minimum velocity that it can have without leaving the circle. So in this case, Newton's second law says net force is equal to the sum of all the forces. What are the forces acting on this? Tension, gravity, they're both going in the same direction, so we don't need to change any of the signs. Force of gravity plus force of tension. Cool. We also know that because it is moving in a circle, when objects rotate in uniform circular motion, the net force, F equals ma, in this case is going to be the centripetal force. It's going to keep it moving in that circle. Centripetal force is V squared over R times the mass. Taking a step quickly back, on your equation sheet, let's say F equals ma. Always memorize that. Use it pretty much in every problem. Centripetal acceleration on your equation sheet is V squared over R. So I just took this and put it in for your acceleration in this case and got V squared over R times M. Cool. Awesome. Now I have two equations, F net. I'm going to set them equal to each other. So now I have V squared over R times M is equal to the force of gravity. I'm going to rewrite it as mass times gravity, because it's on Earth, plus the force of tension. We want to find the minimum velocity, though. So what is the minimum velocity that it can be going, that it will still continue around in its circle? In that case, it will be experiencing no tension at all. It will simply will continue around its circle if at this point tension starts to continue to bring it down. At this point, though, at the very top of the circle, we're going to say the force of tension is equal to 0 to find that minimum speed that it can be going. So my equation, tension becomes 0. Do I have the mass of the object? Yep. Mass, yep. Do I know gravity on Earth? 9.8 or 10. Velocity, what we're trying to solve for. Radius, that just means how far away it is from its point of rotation, 0.81 meters. Only have one unknown in my equation. I will solve for that now. So now I have velocity squared. Do I have to put the mass in, or can I see that this is a term that has mass and this has a term that has mass? Technically, they both cancel. If you did not do that or forgot to do that, totally fine. multiply both sides by 0.81, take the square root, and I get the minimum velocity to be 2 something. Did I do this in my calculator? 2.82 meters per second. So some of you already turned in your FRQs and you didn't write these units. Make sure you write your units. If that's your answer, put a lovely box around it. Cool. Part C. Now you need to calculate the velocity again at point B. However, this time you do have the force of tension as 30 newtons. So the last one we did was at the top of the circle. This time we're going to do the bottom of the circle. Oops. Part C. So at this point here, you have force of tension, you have force of gravity. You know it's moving in a circle, so you have the centripetal force, but you never write that on your actual diagram because that is a net force. Do not write it on the diagram. You can write it off to the side, but make sure it's never touching your object in the diagram. Cool. Force of tension, let's call that positive. Force of gravity, this time they're going in opposite directions, so they need to have opposite signs. Force of gravity, we know mg. Force of tension, it told us it in the problem, 30 newtons. Set these equal to each other. Now we have centripetal force, 30 minus the mass times gravity. Let's do 10 to be easy. Centripetal force. For that last one, we had as v squared times m over r. Plug that in over here. Again, we're trying to solve for velocity at point B here. I think I wrote on the last diagram point A, or point B, but we were at point A. Okay, forget that. Radius, it's still, the string did not increase or decrease. Solving for v, 30 minus 20, 10 times 0.81, 8.1 divided by 2, 4-ish. Take the square root, and you get 2.05 meters per second. Cool. Box that. I feel like as a teacher, I'm so used to saying, do you understand? And then nobody replies except the plant on my table. All right, here we go. Part D. Suppose the string breaks at the instant the ball is at point A, so the very top of the circle. Describe the motion. Oh, has this been a glare the whole time? I'll fix that. Immediately after the string breaks. So here's your point of rotation. The ball is on the string. It's moving around. Oh, it breaks right here. There are no forces acting on it. So the force of tension right here was pulling it in to make it go this way, to make it keep going. The string breaks though, so there's no longer a force that's causing it to continue in its circle. So there's no external force. The ball will continue in a straight tangent line. You can also say it will move horizontally from the point where it broke. It says at that specific instant. We know that gravity will pull it down, so in actual real life, it will break and then start to fall down and follow the path of projectile motion, but they wanted to know at that very specific instant. You could say tangent, horizontal, continue in a straight line, totally up to you. Cool. All right, number 3. This is everyone's favorite pendulum. If you see a pendulum, something that's moving, swaying back and forth, if you see an inclined ramp, if you hear about things moving at constant velocity, is always immediately conservation of energy. Or if it says no friction, no air resistance. Always think of the conservation of energy. All right, here we go. Number 3. Simple pendulum consists of a bob of mass 0.85 kilograms. You have the length of the string. Length, I drew in a cursive L because that is how it's represented on your equation sheet. 1.5 meters. And it's raised to a point Q. So I want you to look at this picture on your equation or on your handout. So here's its lowest point. Here it's at its highest point. It tells you that the height, the change in y, delta y, the height that it is raised to, it gives that to you. 0.08 meters. In the past, sometimes we've been given this angle and the length of the string, and you can find out what this height is. This problem gave it to you. So you already have that. Delta y is also how it is written on your equation sheet. I want you to remember that at the highest point, it stops for a very, very brief second. At that second, the total energy is all in the form of potential energy. It is not moving, so there's no kinetic energy. At its lowest point, energy has been conserved. There's no friction, there's no air resistance, no external force adding energy or taking it away from the system. So at this point, all of the energy is in the form of kinetic energy. From your equation sheet, these are equations you'll use in a couple more problems. Kinetic energy is 1/2 mv squared. Potential energy is mgh. So take a screenshot of that, write that down on your paper, do something fun with it. All right, draw for your body diagram showing and labeling the forces at each point. So when it's at its highest point, point P, we need to draw a dot again. It's on Earth, so there's gravity. It is not touching anything. So remember, if you had a box sitting here on a surface, you have gravity pulling it down. And if it's in contact with something, the floor is also exerting an equal and opposite force, which we call the force normal, only if they are touching. This bob is only touching the string, so we don't care about the normal force. We do care about tension, though. Tension is a force that we will label as such. At this point, it is being pulled at an angle, so force is at an angle as well. Point P, and what else do you need? At the lowest point. So down here, again, we're going to draw this dot. It's on Earth, so we have gravity. It's not touching anything. We have force of tension. Cool? Cool. That's all you had to draw. All right, part B. You need to calculate the speed of the bob at the lowest point. So again, we're going to use conservation of energy. We know the total energy here is in the form of potential energy, and here it's kinetic. I see velocity in this equation. Don't see it here. Because the energy is conserved, though, all of this potential energy has been converted into kinetic energy. So if we know this, total energy up here, we can find this and subsequently solve for velocity. So total energy, set them equal to each other. mgh is equal to 1/2 mv squared. These are all multiplied by each other, so I can divide both sides by m. Those cancel out. Do we have the height? Yep, already given to us. G on Earth is either 10 or 9.8. Velocity is what we are solving for, so we are good to go. Multiply both sides by 2 to get rid of your 1/2 and take your square root, and you get velocity is equal to 1.25 meters per second. Cool. If you don't have a calculator, you can use Desmos, or there's a great calculator app for the TI 84, I think you have, that you can get on your phone. AP knows that you are going to be using your notebooks, using your calculators, using your phone, so do not feel penalized or whatnot for using Desmos or another website. Cool. Now we need to find the total energy of the oscillating system. So oscillating, remember, just means it's going back and forth on forever. The total energy I see is right here, and I also see is right here. I know the mass, I know the velocity now, so I can use this equation or I can use this one, up to you. Maybe you want to use this one if you already have it in your calculator. You can just press square times 0.85 times 0.5, up to you. Let's use total energy at the top, just for fun. The mass is 0.85 kilograms, no need to convert. And the height. Ooh, did it give us an angle? Did it give us a length? We have the length, but not the angle. Oh, but it already gave us the height, so no need to convert there. Plug that all into my calculator, and I get 0.7 capital J joules. Remember, energy is measured in joules. Cool. All right, part D. You need to find the height. Determine the height at which the potential and the kinetic energies are equal. So I know that the total energy is 0.7. I want to know, and I know that the only types of energy in this problem here are potential energy and kinetic energy. So I want to know if it starts with 0.7 joules of potential energy here, when does it get to half of that amount of potential energy, assuming that all of the rest of the energy has been converted to kinetic energy. So I'm going to do when half the energy, total energy, is 0.7, so half of that is going to be 0.35. So what is the height when the total energy, the potential energy, is 0.35? Joules is equal to mass. I need to find that height. I could, maybe you're thinking that you should use this. Oh, when kinetic energy is at 0.35, which is half of this number, but would this equation have given you the height? The answer is no, you only have velocity and mass. You need to use potential energy because it has height. Cool. 0.35 is equal to mass. G on Earth is 9.8, and the height. Awesome. One unknown in our equation with some other numbers. Plug those into my calculator, and I get height is equal to, 0.04 meters. How does that compare to this number? Exactly halfway down. So potential energy, they have direct relationships, so it will be half of that height there. Cool. All right, part E, you need to draw a graph. We love drawing graphs. So draw potential energy versus a horizontal position graph. Immediately think to yourself, if there's graphing, you need to use at least half of the area to get those points. And label will get you some free points as well. I'm going to keep my picture there. It's part E. All right, so you need a graph. It says horizontal distance. So we only care about this here. Let's say this is negative x. Let's see here, this is 0, and here this is x, the furthest distance it gets. So here on our graph, we have the same thing, 0, horizontal distance, it gets to some positive value x over here, and some negative value x over here. I saw some of you drawing this as already as not having this part of the graph, that we're just saying like, oh, the horizontal distance starts here at 0, and then we say this here is 0, then this would be x, and this might be 2x kind of thing. You need to make sure your graph reflects that. But we're going to define this middle part as 0. So here is the equilibrium position. It's going to go to x and negative x. All right, at negative x in its horizontal direction, all of the energy is in the form of potential energy. It's going to be at its highest point. So here is potential energy. Negative x has lots of potential energy. That's the most amount of potential energy it'll ever get. As well as when it gets back over here at this point, it's going to have the same amount of potential energy. So it doesn't gain or lose any energy. At this point, when it's at its lowest point here, the potential energy is 0. Why? lie because all of the energy has been converted to kinetic energy. So I'm going to draw a dot here. Cool? And like so, connect the points. There's your graph. All right, the last part, F, it says, what can you do to increase the period, right? Double. You need to double the period. So I'm thinking to myself, I know T is equal to period. I know in my equation sheet there's actually an equation for pendulums, so objects that move back and forth. T pendulum from the equation sheet is equal to 2 pi square root of L. L, remember, is the length, if I can spell today, divided by G. G is equal to gravity, acceleration due to gravity. So it says, how do you get this side of the equation to be, you want it 2 times bigger. So if you want this side of the equation to be 2 times bigger, you need to make this side of the equation 2 times bigger. The way you can do that, yes, you could transport it to a different planet. However, simply put, that you could do right now, you can change the length of the pendulum. So maybe you're thinking to yourself, oh, I'm just going to double that. If I put 2L in here, I double the length of my pendulum, that is going to only increase this side by the square root of 2. Do we want to increase this by the square root of 2 times bigger or plain 2 bigger? You want this 2 times bigger is your answer. So I need to make this length 4 times bigger. Why did I put that 4 under next to the L? If you make the length of your pendulum 4 times bigger, this term is under your square root. So you will square root 4 and you get 2. So if you get this side 2 times bigger, technically the square root of 4, your other side will be 2 times bigger as well. And that is it. And we finished in less than 45 minutes. Okay, cool. Please text me or call me or email me if you have any questions or if you have feedback like, I can't hear you, these are silly, please don't do these again, or say like, hey, can you write bigger or color coordinate them? Please, love the feedback. Awesome. Talk to you later.